All right, if you look on your calendar, today is the 24th. It is the 24th. Today we are supposed to begin discussion of springs, simple harmonic motion, and more dynamics. Okay, we're gonna skip that and jump straight to date on the date 29. September 29th. We will come back to that. Okay, we're gonna come back to it. We're not gonna neglect it. I'm gonna cover circular motion first. And all right, we're gonna talk about circular motion. This year in Physics C, circular motion is very similar to last year in Physics B. Okay, remember, we've already talked about this. How many types of acceleration are there? Okay, in nature, there's just one, right? There's just acceleration, right? But what we do is we split it up into two kinds of acceleration because mathematically it's easier for us, okay? So our two types of acceleration are our linear acceleration or tangential acceleration, we've been calling it. All right, our tangential acceleration is the acceleration that we think of most often in our everyday life. It's the speed up or slow down kind of acceleration where you're changing your speed, so therefore you're accelerating, okay? So change in speed over change in time, okay? Now, we think of this algebraically really as acceleration is dv dt. Now, technically, dv dt incorporates all the acceleration that there really is, okay? If you're doing this calculation vectorially with vectors, then when you do that calculation with vectors, it will give you the real acceleration, both tangential and radial, both the change in speed and the change in direction, okay? But when we think of this, most of the time, we think of this algebraically. We think of this just as the numbers and not as a two-dimensional or three-dimensional thing, vector derivative, okay? So when you see dv dt, the way we normally think about it in this class is just that that's the algebra version of that. We're just changing our speed, okay? We're not really changing our acceleration, okay? So, yeah, sorry, we're not really changing our direction. Thank you. So, remember that acceleration, tangential acceleration, is always parallel to the path that you're going. So if you have some object that is traveling in some weird direction like this, that first of all, remember velocity is always tangent to this path, no matter what, okay? And this type of acceleration will be either with or against, parallel or anti-parallel, with the velocity. So it's either going to be like this, or tangential acceleration like this, or like this, if we're speeding up or slowing down. Okay? Does that make sense? Yeah. All right. So that's kind of what we think of as acceleration for the most part. And then in Physics B, actually pre-AP or first year physics, we start talking about centripetal acceleration, but most times it doesn't sink in for a little while. Okay? We have this radial or perpendicular, or better yet, centripetal. Acceleration. Okay, now centripetal acceleration is change in direction with time. Okay? Change in direction with time, and we can go through the derivation, if you'd like, of how they come up with this, but I'm just going to give you a real brief outline of why this always points towards the center. If you have something going around a turn like this, okay, its velocity is this way, velocity 1, and here is velocity 2, okay? All right, so everybody, real quick, tell me, which way is the direction of the change in velocity? Okay, so if this was our initial, and then we have some change, and we end up with this as our final, right? Our delta V is equal to V2 minus V1. Now, these are vectors. So V, well, let's just do it that way. It'll be easy to do it this way. So here's V2. V2 points this way. Which way does V1 point? Points this way, right? But we want a negative of it. So which way does that point?
Down.
So it means like V2 plus a negative V1, right? Which would be the opposite of this one, which would be this way, right? There's V1. So what's our delta look like? Delta V. All right, so you can think of it vectorially, if you'd like, in a picture. And our delta V points down. Now remember, since delta V divided by t is our acceleration, this is our acceleration, okay? Our acceleration, or the direction of our acceleration, and our direction of our acceleration is downward. Okay, now think calculus. Okay, think calculus. Do this calculation as time. No, let's do it this way. As delta V gets smaller, goes towards 0, or as our time period that this occurs goes towards 0, I should say, probably. Okay? That's probably better. All right? As these two get closer and closer and closer together, okay, which direction does this delta V point then? All right, if I put this one here and this one here, okay, V1 and V2, it's still pointing down, right?
Yes.
Still points down. So what happens when I get this V1 and V2 so close together that they're right there? It points this way, right? So our delta V is pointing that way, and our V is pointing that way when we're changing direction. That means our acceleration is downward, and our centripetal acceleration points always perpendicular to the velocity, and it always points towards the center of the circle or the arc that we happen to be in. Okay? So that's kind of a little hand-waving explanation on where it comes from. But this always points towards the center, which is centripetal, center-seeking, right? And so that one here would point this way then. Our centripetal acceleration or our perpendicular acceleration. Okay? And this one's going to point, well, if I'm on a straight stretch here, I wouldn't have any, right? It's not turning here for straight stretch here, but this one's going to point this way. Okay, so when it's not turning, there won't be any. So if this is kind of straight here, and this is kind of straight here, then there would be no centripetal acceleration. Okay, but right here there would be centripetal acceleration this way. Okay, so it's turning towards that direction. All right? Now, last year our turns were always perfect circles. They do not have to be perfect circles. You could have any kind of turn you want, say like an ellipse, okay? And the centripetal acceleration will always point perpendicular to whatever the tangent line is, right? So the tangent line right here looks like that. So our velocity is going to be along that tangent line, but our acceleration, centripetal acceleration, will be perpendicular to that, right? All the time. So it's not going to be pointing towards a single point in this kind of case, right? So we're pointing to different locations. Just the center of the immediate arc. All right, so there's a couple examples on the front of page 1 of that thing, right? Where a car going around a turn and an object going around the sun. Blah, blah, blah. We've talked about everything on page 2, I believe. Okay? Okay. Quick thing. Sometimes a trick question. This usually shows up, this trick question usually shows up in Physics B, but I don't know, it could show up in Physics C as well. The question of, you've got a car, and you're looking down at the car from the top, and see here you're sitting there driving, and you got a package sitting next to you, and you make a turn, and the package scoots to the right-hand side of the car as you go around the turn. Okay? Now, they give you lots of different options in this multiple choice question, like there was a force that caused it to move outward to the right, or different things like that. Or they would say something like, well, the seat was frictionless. or they give you lots of different examples of why it would occur. But the deal is why does this, while we're in the car, have this mysterious behavior of scooting outward? Yeah.
Why would anybody have a frictionless car seat?
Good point. That would be a very dangerous car. The old vinyl seats. See, you're not aware that the old seats, they used to not be cloth, they used to be vinyl.
I have vinyl seats in my truck.
Do you?
Yeah.
Yeah, some trucks have it just because they're easy to clean up. Like if they're work trucks, they still have vinyl seats. But most cars don't have those. But yeah. No, but they can be kind of frictionless if they get old and slippery. All right. So why does it slide outward? Well, if you're in the car, it looks like there is a mysterious force pushing it outward, right? And actually, if you're in the car, there appears to be a mysterious force pushing you outward, right? Flinging you to the side of the car. Yeah. Whoosh. And you'll see that all the time if you read stories like this car. There was a car crash and the person was thrown from the vehicle.
Right.
Like somebody threw them out. Okay. No, no, no. All they're doing is maintaining their velocity. Newton's first law. An object in motion wants to stay in straight line linear motion.
Could you imagine this
The driver
the person
maintains
maintains
Yes.
the vehicle
Instead of saying the victim was thrown from the vehicle, they should say something like, yeah, the car inadvertently turned and left the
left the victim
uncompanioned, by the vehicle. That's right. So yeah, they left.
Journalism.
That's right. We'd be horrible journalists.
They'd be like, I can't understand any of this.
All right. So what happens is the object wants to just go straight because it has inertia. Objects in motion want to stay in straight line linear motion. So when you make the turn, if there's nothing there to stop you, you'll go straight. You can try that sometime. Take the door off your car.
Let go.
Or drive like a UPS truck.
Yeah, drive a UPS truck or the old, even the new mail trucks. With the doors back.
Get out and
Jump out, yeah.
Okay, the diagram on page 3. Everybody see that?
and the little V.
With the tiny V.
What are you asking?
It's just not that important to the equation, I guess.
That's right. It's a little velocity. Okay, everybody remember that when you're going in uniform circular motion, that your velocity is tangent to the path, right? Your acceleration will be only centripetal towards the center. And your force is centripetal force. Now, a couple of things. Let's write this down. Our centripetal acceleration is v squared over r, which we learned last year. Okay? Remember that our tangential acceleration is dv dt algebraically. We're not talking vectorially, because if you do vector math right here, then it incorporates both of these all in one. Okay? All right, so tangential and centripetal, that means our total acceleration, actually just A, right, equals dv dt squared plus v squared over r squared square root. Okay? That's the real total acceleration of an object. Okay? Right?
Yes.
You should write that down because that's not in this. This was for physics B. This little packet I gave you. Okay? Now, I'm confident that you can all do your derivatives. Piece of cake. I'm confident you can do v squared over r. Just remember, if the object is going in a circle, the velocity of something going in a circle is still just distance over time, right? Or displacement over time. You should say distance over time, otherwise you get 0 for a circle. So it's circumference over time. So 2 pi r over the time period is the velocity of this object, instantaneous velocity of this object. All right. If you prefer, you can have that 2 pi b over t. Or 2 pi rf. What the heck's that? 2 pi r.
Because the
F.
base and the frequency and then multiplies by.
Right, because frequency is 1 over the time period, right? Now how do we convert that into omega? I want to get rid of the v.
B equals omega r.
All right, so
I would totally do that by units.
v equals omega r. Now let's check that because like most of you like me, you don't use omega a whole lot, so let's make sure we got this right. What's the units on omega?
Meters per second.
Rads per second. What's the units here?
Meters.
Meters. So do I get meters per second? All right, so check. That looks good. All right, so v equals omega r. So let's convert these things into, what if we have an omega? All right, so right here, first off, centripetal acceleration in terms of omega will be what?
Omega r squared over r.
So omega
Omega
squared
squared
r.
r.
It'll be omega squared r squared over r, which is omega squared r. So you need to add that to our little packet. So omega squared r, and that comes in handy. Omega squared r. All right, so we got that going for us. All right, so, okay. If v equals omega r, and that equals 2 pi r over t, then how do we figure out omega?
Is it 2 pi over t?
Yeah.
It's 2 pi over t, right?
That's cool.
Now, what I would suggest for you is that during the test, if you run across some of these things, some of you will remember that and some of you won't, and that's okay. If you don't remember it, remember some of the basic ones and then just derive it. Okay, it's not that hard. Okay, how do I put this in terms of this one right here? In terms of frequency.
2 pi f.
2 pi f. And we've done that one before. And that should make sense, right?
Yeah.
Because the frequency is like revolution or complete circle per second, right? And omega is in rads per second, and there are 2 pi rads for every full revolution. So you'd have to multiply frequency times 2 pi to get you your 2 pi rads to make one complete circle. All right? So there's our conversion there. Okay. So we're left with the magical F equals ma. Okay? And if you're going in a circle, then you'll have a centripetal acceleration and you'll need a centripetal force. Okay, everybody, please remember from last year that centripetal force is not a magical new force. There's no such thing as a centripetal force. Okay? Centripetal force is just the name that we call this combination of forces that causes us to accelerate into a circular path or into an arc. Okay? So, this could be anything. Gravity, friction, tension, normal force. Combinations of these things can make this. All right? All right, one big trick question, I show it there on the bottom of page 3, is that how much work is done.
Zero.
Yeah, if something's going in uniform circular motion. So if we have the sun here, and here's a planet, the planet's going around in a circle. Remember, it's propagating that way, and the force of gravity is this way. They are perpendicular. And remember, how do we figure out work from last year? F delta r cosine theta. What's my theta? 90. So it's moving that way, right? So that's 0. Cosine of 90 is 0. So work is 0. So mathematically it's 0. Also philosophically it's 0. If the object is going around the circle, what does work do to an object? Work either adds or subtracts energy, right? It's the transfer of energy. So the deal is as this planet is going around the sun in a perfectly circular orbit, does its energy change? Kinetic stays the same, potential stays the same, nothing's changing. So there can be no work done. Okay? Now, it's not like it's not doing anything. It's causing it to go in a circle, but it's not doing any of this thing we call work. It's not adding or subtracting energy from it. But what about an object that goes like this? We'll talk about this later. What if it goes in an orbit like that?
It's gonna work. You said that it's 90 degrees, right? It's perpendicular, but its speed has to speed up, right?
Ah, okay, so here's the deal. At this point, the velocity is this way, and the force is this way. So therefore, at this instant, there's no work. Where else is there no work done? Over here, right? Where the velocity is this way, and the force of gravity is this way. By the way, both of these will be much bigger here. I haven't drawn them to scale. It'll be going much faster here, and the force of gravity going much bigger because it's closer, right? All right, now right here, velocity is this way, tangent to the path. The force of gravity is this way. Now, what did I say is always perpendicular to velocity? That's the centripetal acceleration, right? This force of gravity is the net force, which causes our two types of acceleration. It causes us an acceleration this way, which is our centripetal, which is perpendicular, and it causes a component this way, which is tangential. So this part of the acceleration, or part of the force, causes it to turn. The other part causes it to speed up. Everybody, this causes it to turn. This causes it to speed up. When you're on the other side over here, you get the opposite. Oops, I lost my red marker. You get the force this way, which causes a tangential acceleration this way and a centripetal acceleration this way. So it slows down on this part, speeds up on this part. Now, I will accept two answers then for this. Does the sun do work? The answer is, well, yes here, positive work. Yes here, negative work. But no work at this point and this point. But if you take from here all the way back around, what's the net work?
0.
Yeah, the net work for the whole complete circuit is 0. It cancels out. All right. There are 3 types of uniform circular motion problems. Now, we will end up with some problems that are non-uniform in this class, so you need to be aware of that. But these are the 3 types of uniform ones. There is this first type on page 4 where you have a single, one and only single force that causes something to go in a circle. Okay? Like for instance, in the amusement park ride where you're stuck to the wall as the thing spins around, the floor drops out. That's the normal force. Okay? For the sun and a planet, that is gravity. For a car going around a turn where the turn is not banked, that's friction. Okay? Very easy. Single force causes mv squared over r in your equation. All right, our next type is where you have a force that is only part of the force causes you to go in a circle. And the 2 common ones that we have are this one right here that you see a lot, the conical pendulum, which is just the swing ride at Six Flags, where you get the swings and they spin you around.
Or tetherball?
Yeah, or tetherball, same thing. Or tether cat, if you remember from last year.
What?
You haven't seen tether cat?
I do not want to be slapping on those cats and make them go around.
I don't want to be slapping on no cat.
Exactly.
This ain't no English class.
Exactly. No, I'm kidding. I don't want
Tension,
to be a cat.
mg, going around in a circle. Okay, everybody right here. Which way is it accelerating? Towards the center. So we set up our coordinate system like this. X, Y, because we're accelerating this way. That means we break tension up into components. That means this part of tension equals this here because, or the mg, because you're not accelerating up or down. That means if this is my angle theta, this t sine theta equals mv squared over r, right? That's our f equals mac. And there you go. The banked turn, the NASCAR turn, is the same thing. Okay? Now we're going to make that harder this year. So let's do that. Because we can. Because you're smart enough to do it this year.
Because we're cool physicists.
That's right. because we want to show off to others that are lesser than us, right? Oh, I'm sorry. That sounded kind of pompous. I'm sorry. All right, let's do our bank turn like this just because I want to mess you up. Because you usually see the incline this way, and I'm going to draw it this way, just because I can. So here's your car. See my nice car here? Oops, I guess the antenna would swing the other way, right? As you're going around the turn. And you have a little jack ball on the end of that thing. Alright? There you go. It's the back of your car. Nice rectangular car going around a turn. Okay? Alright, draw all the forces on it, please.
You want to turn it on an incline? What is that?
Never drawn on it. You mean
That is a car going around a curve.
which way
So it's
is
going
drawn
around
on
the
it?
inside or the outside?
Yeah, which way is the curve? The curve is not this way. Come on. The curve is this way.
Oh, that's kind of what we used to see on it.
Go around a turn like that. Come on.
I got it.
Okay, draw the forces.
I got it.
What?
How you meant that you were gonna do it differently.
What would happen if you had the
We're so
outside?
used to that.
If you go too fast, you will.
Yeah, because your weight would have to.
Yeah, you'd slide outward. You
That'd be a harder physics.
would not be good.
On that one, if you increase the tension or whatever the angle.
Yes. Good point. Everybody, if you take this one right here and you spin it faster and faster, what happens?
Start going on.
Okay, if you spin it faster and faster, the tension has to get bigger, right? How does it accomplish that?
It rides
Oh, because
Your
gravity
radius
is
is small.
your
it's
angle.
not
So it's just tension.
Well, the string, you just pull it harder and the tension gets bigger, right?
Okay, because the
But the thing is does this part of the tension change?
No.
Okay, so while this part of the tension stays the same, this part of the tension has to get bigger. So what does that mean for the ball?
Right.
It rises up. Because the vertical part has to stay the same size.
Why?
Because when you spin it, the ball doesn't accelerate up and leave, right? Actually, the answer to that is it does accelerate up. As you spin it, as tension grows, it accelerates up, but then it reaches this equilibrium point where if the angle gets too high, then this part of the tension is less than mg, and mg pulls it back down. If the tension on this side is too low, then it will accelerate down. If the tension on this side is too large, it will accelerate up. So the angle self-adjusts itself to the speed that you spin it and whatever the mass is.
So is it possible for you to spin it perfectly?
Actually, no, the mass doesn't matter. I think the mass cancels out if I remember correctly. So it doesn't matter. Yeah, because if you look at the ride at Six Flags, the children and the adults on the swings, they don't swing at different angles, right? They swing at the exact same angle. The mass cancels out.
So, but could you, like, I guess you can't spin it horizontally?
Yeah, so can I take a ball on the end of a string, or can we speed that Six Flags ride up really fast and get all the children horizontal? Can we?
I'm sure if you really wanted to.
Well, but he's saying no. 'Cause
Now,
if the tension,
We can't, because there's always got to be a vertical component of tension. If you get them exactly horizontal, then mg is down and tension is horizontal, and so it'll dip. Now, it may not dip much, but
So it
yeah.
goes like
Yeah, and then they'll reach an equilibrium. Okay? In fact, if you've ever field trip, Six Flags, get on that ride, and as it spins you up, you'll notice sometimes that you'll swing back and forth like this across that equilibrium point.
Can we have food with the Six Flags when we do K-612?
How about we just put you in a chair and get some chains and we'll spin you?
Yes.
No, I think
The same day you shave your head.
Right.
Next Tuesday, bring your
Now,
I have to take
they can get you, spin you and then turn you vertical, and then you would be directly out. All right. Okay, everybody, what are the forces on this thing?
normal.
friction, maybe.
Okay, now, here's the deal. You can make this turn with no friction if you want. Which way are you accelerating?
To the
This way. So which way do we make our coordinate system? Okay, now everybody wants to make your coordinate system this way because you're used to doing that with inclines, but you're not accelerating this way. You're accelerating this way. So you make your coordinate system x, y, which means that,
Like if you bank it enough, you don't need friction.
yes. Actually, for every bank turn, there's a design speed for which there's no friction necessary. So you can ice the road down, and if you hit it at that right speed, you'll go right through the turn.
But in Texas, it's like 10 miles per hour.
Yeah, they're not banked. Like on a highway, the design speed's something like 60 miles an hour, I think, usually. I don't remember, for the bank. So most people drive 80, so if there's ice, they'll slide out.
And if you're driving 60 on an icy day, pretty awesome.
Slippage, oh gosh. no.
Yes, slippage. All right, so we break this one up. So wait a minute, what does that mean? Which one's bigger?
So it's like,
No, which one's bigger, normal or mg?
Normal.
Normal, because this equals this.
That's just
Therefore, normal must be bigger. Now wait a minute, that's if you're driving at the exact perfect speed where no friction is necessary. What if you drive too slow? Which way will friction be? Which way will your vehicle want to slide?
up towards the wall.
It will want to slide, if you're driving too slow, your car wants to slide down the incline.
Yeah.
So which way will friction be? Up the incline. What if you drive too fast? Which way is friction? Down, because you want to slide outward on the turn, right? So let's say that you drive too fast. Or as they say in Dr. Seuss books, too fast. Driving too fast. Too fast. Okay? Which way's friction?
down.
Okay, now everybody.
Yes.
This makes for a hard problem. Why?
Because it doesn't look like
The coordinate system is off.
Because your coordinate system is not matched up with friction. So what do you have to do with friction? Oh, no.
Oh, no.
Well, yeah, what angle? I was
It
confused.
doesn't
Angle.
Mr. Brilliant.
How does that
Mr.
work?
Brilliant. But,
Let's
okay,
go back to
you said
geometry
earlier
again.
we're gonna put our coordinate system like that because of acceleration, but now that two of our forces are overpowering the acceleration force, or not that overpowering, but I mean they're more than
Yes.
that in the other coordinate system.
You are correct. We're breaking up two of the forces into components, and the question is, well, wouldn't it be easier if I just set my coordinate system this way? That way, this one and this one would be lined up with my coordinate system. I only have to break this one down. But then you'd have to take your acceleration and break it into components.
So the same thing.
Yeah, see, probably not worth it, because the thing is your acceleration is going to be a centrifugal acceleration, break it into components. Ugh. All right, so here we go. Everybody, here's what I want you to do. For this problem, we're going to solve it two ways. We're going to solve it at design speed, or what is the design speed? Okay, what is the design speed? Giving this angle as, here, 40 degrees. We're in NASCAR. All right, and then the next thing is we're going to say we go too fast.
But at design speed, what happens?
At design speed, what does that mean? No friction necessary.
Okay.
Okay?
Mr.
All right.
Aaron, my brain just exploded. If you're going too fast,
Mhm.
your
Hey,
car is
sit down, you.
like, wanting to move to the outside.
Your car wants to go straight, and there's
Right.
not enough normal force to make it turn. So
So
therefore,
there
you
will be-
need extra force.
And the friction is it?
The friction
Static?
is at, you want it to be
I
static.
do. You
Right.
guys do not.
Because I do.
Right. Ah!
But you're moving.
Yes.
But it is static friction.
Yes.
It's not moving. It's like
Right.
You're not moving up or down.
That's right. You're moving, but the friction we have there is static. Very good. Because otherwise you'd be sliding out of the turn, right?
Okay.
All right. Come on, let's get moving. Let's leave the rest of those people behind that aren't here.
No, we can't do that to them.
She's a liar.
All right. So there's no friction, or at least no friction necessary. All I'm giving you is the fact that this has a mass of m. And we have a bank of 40 degrees. And that's it. Okay? Son Hank, wake up, dude. Alright, so here we go.
What is design? Like, what does that mean?
Design speeds, it means that you can go around the turn without any friction necessary. Okay? So a lot of times they'll say, like, you're on an icy road, or you make the turn without any frictional force. Okay? All right, so what's that?
Wouldn't that feel weird? It'd feel like you're driving straight.
No, actually, it would feel like you're driving straight, except it would feel like you're a little heavier because you're accelerating more than just G-force, right?
Yeah.
You would feel extra. So you would sink straight down into your seat a little bit, but you wouldn't have a tendency to be pulled or pushed one way or the other.
That's cool.
If you go around a turn too fast, you'll be pulled this way in your car. You'll be pulled. I made it bad. Centrifugal force. You'll feel like you're being moved to the outside of the turn. If you sit on an incline like this, you've done that in your car. Sometimes you parked in a parking lot that's banked or something, or on the side of a hill, and you want to slide down this way, right?
Yeah.
So if you go at just the right speed around that turn, you'll feel nothing except slightly heavier.
That's so cool. Can they
Now,
simulate
in
that?
NASCAR, or actually in NASCAR and Formula One, as they go around these turns, they can get like 2.5, I think they can even get to 3 Gs in some of the turns. And so, yeah, and they're not flipping over. And because they had problems with the Texas Motor Speedway with the NASCAR, with the Formula One, because they were going too fast. Because it's banked so high, and they could go so fast that they were hitting like 3 Gs or something, and the drivers were kind of starting to black out. Isn't that right?
It's crazy.
Yeah.
I used to keep doing that, you know?
I would like for you to draw, we break this up into, or write F equals MA.
Wait, twice on the same time.
We write, or build both of these for both directions, X and Y.
Oh.
Okay? In the X direction and the Y direction. Okay?
It's the same thing as mine, just like switch the way.
Yes. Okay, can you do it? It's like it's done right there. But could you do it? Okay, in the Y direction, what do you have? You've got an,
So wait, we're not using friction force because you
yeah, there's no friction.
But we're driving too fast.
Hang on. We're going to do this one first, and then we'll drive too fast.
Okay, so we're not having.
Yeah.
Okay, so it's
Okay, in the Y direction, there's no acceleration, correct?
Right.
There's no acceleration, right? That means this equals this. That means mg cosine theta equals m. No, I messed that up.
isn't it like
Normal force.
yeah, close to theta.
Normal force cosine theta equals mg.
Yeah.
Sorry about that. That was my mistake. All right, so go over here then. In the x direction, we have one force only. Fn sine theta equals mv squared over r. Okay? All right, now, I do not know the normal force. The only thing I gave you was m and theta. So let's get rid of the normal force. How do we do that?
MG cosine theta in the y direction is
This one? Oh, solve it for normal and then plug it in? Okay, we can do that. There's another fancy way to do this too. It doesn't always work. It happens to work in this case. If you take this and divide it in over here, you can do that all at once. I'll show you that in a minute. Force normal equals mg over cosine theta. Take that, plug it in, and when you come over here, you get mg tangent theta equals mv squared over r.
G10.
You get g tangent Theta equals b squared over r. Okay, now, g is given, theta is given. The only thing, we need to know one more thing before we know the design speed, right? And that's the radius of the turn. Okay? So, what do you think the radius of the turn is for like a NASCAR turn?
A couple.
Of 100 feet.
100 feet? 100,
No, that's not very far.
100 meters?
500
Yeah.
meters.
That'd be about 300 feet. Okay, so let's make the radius of this turn 100 meters.
Where
okay?
does that radius end though? Like when the
Okay,
bank starts?
if you're looking at it from the top, it would be like this. If this is the turn, then from here to, I'm doing it to the center,
Okay.
wherever the car is. Okay, that's your radius. Okay. All right. So let's say that that's 100. So what's our design speed? I don't know. I'm making this up, so we'll see if we designed a good track or not.
Oh, wait, 100.
We're making our radius 100 meters.
So just when you're doing, what's the design speed at the change, you just don't factor in friction? Oh, wait, what?
Yes. Or, like I said, they'll say something about
I got
no friction is necessary to make the turn.
28.676.
What do you get?
28.676.
That's a horrible NASCAR turn.
Okay, well, he's like separated
Let's see.
X and Y.
9.8.
So the sum of
Wait, what
forces
do you
is
do?
140. Are you in degrees?
Times 100. Yep. 28.7 meters per second. Okay, that's not very fast. That's, I don't know. Because 45 meters per second is 100 miles an hour. Okay, so we're not, we're maybe 60 miles an hour maybe. What did I say, 28.7, is that right?
Yeah.
Meters per second. Okay, there's our design speed. Let's say that we're obviously late for school and we're going to drive a lot faster than that. So let's say we drive too fast. So let's say that our too fast speed is 40 meters per second. You know what, let's not make it 40 because that's going to confuse us with our 40 for our angle. Let's make it 50. 50 meters per second. Let's see if we can do that. 100 meters per second. 50 meters per second already is 100 miles an hour. Or 100, more than 100. Okay?
What do you want us to do with it?
What if we were going twice?
All right.
Wait, Mr. Bruin, just to confirm what I'm doing, I got 28.7 kind of, except the decimal is like 0.287. I don't know what I did.
Did you rank?
Mine is 28.67608113.
Yes, except I have that except with the decimal on the left.
Times 100.
You forgot to multiply it by 100?
Why do I do that?
Because the radius. Right here.
Oh, I divided by 100 instead of multiplying.
There you go. That'll do it.
I don't know why I was dividing. Times 100.
But see, that's when you work through a problem and you get an answer. Just remember, your calculator is only doing what you tell it to do. So a lot of times most of the time, we really need to go through it, kind of think about what our number is when we're done. It's just kind of, is that reasonable? Does that make any sense? Because sometimes you'll catch a mistake like that before you actually put it down and get graded on it. All right, let's see. Could we go 50 meters per second? Okay, if we go 50 meters per second, what changes? You need friction. Which way?
Up.
Up?
Go down because you're going up, sorry.
Yeah, it goes on the swing, yeah.
Can you what?
We go 54.7 meters.
Why?
That's twice as fast we should be going.
You want to go twice as fast?
Yeah. But then we won't know how to do it when it's not twice as fast.
We'll just do 50. It's easy. All right. Now, what changes in our equations then?
You have to put in friction.
All right, so, this goes away. Let's start over.
Okay.
So here we go. Now, in the y direction, what's our equation in the y direction now?
Fn cosine theta minus F.
If,
Friction.
if
That's what
the
that.
sine theta was.
What?
What? What is that? Oh yeah.
Oh, yeah,
Okay.
that's true.
You did the MG first. Okay.
Yeah. You can have this one up minus these two down equals 0 if you'd like. I just put my negative ones on the other side. All right? So there you go. What kind of friction is this?
Oh,
Static, right?
Static, right?
Yeah, but I don't know why.
Why?
Because you're not moving.
Because it's trying to,
Because
That's a design.
if you had kinetic friction, that means your car is sliding out on the turn and you're not making the turn.
Are we gonna do that?
We're going to check
Oh,
to see
it's
if we can
static
go this
friction,
fast.
you're not moving it, you're just trying to.
Yes, your car is trying to slide this way, up the incline. Which means that your car is trying to go this way, but you're trying to go that way. So your car is trying to slide up and out of the turn, up the incline. Okay? All right, let's draw our, what's our F equals MA in the X direction look like?
Theta.
F sine
Okay.
Okay?
Z.
minus F
Plus.
Oh, I
cosine
guess.
theta, right?
Wait,
Minus
wait.
F cosine, well, plus.
They're going in the same direction.
Oh, that is true.
F cosine. Good.
Yeah. Come on.
MV squared over.
That way? And that way.
Okay.
Right? So your friction's helping you. That should make sense. Because if you're going too fast around the turn, you need something
Oh, yeah.
extra to help you,
That
right?
makes sense, that makes sense.
All right, and then we get an mv squared over r. Okay. We don't know the normal force again, right? What do we know? We know angle, we know m, we know v, we know r. We don't know normal force, so we have to solve for normal force and plug it in.
because it's the hypotenuse. Okay.
Got it?
We don't-
Good.
We're just catching up.
No, that's okay.
Hold on. No friction. We don't know anything about friction is.
That's right, we don't know friction. We're going to solve for what friction would need to
Oh,
be.
okay.
Oh,
Okay?
I have to think about
All right, so force normal equals mg plus force friction static sine theta over cosine theta.
Yes.
That goes in here, which gives me mg plus force friction static sine theta times
Sine.
tangent of theta,
You can do that too.
right?
Yeah, you can do
Yeah.
that.
Because this all gets chunked in over here. The sine over the cosine gives me a tangent, and it gives me this, right?
Yes.
All right. Plus force friction static cosine theta equals mv squared over r.
Are we gonna be able to use identities in this place?
Trig identities? You bet. Do we have any that'll help us? What's a
Well, no.
sine tangent?
Nope.
I don't know.
I think so.
I was just asking.
Nine squared over R is eight.
No.
The sine cosine is a sine 2 theta, right?
Yeah, you're right.
I think that's right.
But,
Okay. Do we know all these things except for friction?
Yes.
We sure do. Okay, will you please solve for what's friction? What would our friction force static need to be?
So that's what we're solving for, is what friction we need to be to go that speed?
yes,
What would our friction force need to be in order to make that turn?
I don't know.
And then we're going to decide, or try to decide, if that's possible. Whether that's a reasonable thing to
What's M?
M? Aww.
M cancel out.
We don't know what M is, do we?
It can't do that.
Drat.
Does M cancel out? No,
It
it
doesn't
doesn't.
cancel
No,
out
not
with
this
this,
time.
but it cancels out.
M
with
doesn't
this.
cancel out this time, does it?
I guess you don't have to do it.
500 kilograms. Let's see, what's a car weigh? About a ton?
A car was a
My weigh's 2 tons.
You drive a tank? All right, let's make the mass of our vehicle 1,000 kilograms.
Well, unless
12.
851.8.
Why,
Okay, we would need 12,852 newtons of force. Is that correct?
Yeah.
Frictional.
Frictional force. Yeah, I think we're gonna die. Let's find out for sure.
The coefficient of friction is like 1.3.
Okay, well, now hang on. In order to find coefficient of friction, because to really find out whether this is possible or not, we need to know if we can have that much friction. So how do we do that? Force friction static is less than or equal to mu force normal. But what's our normal force? Is this. This is our normal force.
Oh,
never mind.
Okay? Notice our normal force is going to be quite large. It's not just mg. So we might get it,
Nice.
but I'm thinking not.
Makes sense.
Yeah.
Yes.
So this is going to be, what, 1,000 times 9.8. Our frictional force here is 12,852 sine of 40 divided by cosine of 40. What's our normal force?
23,
Today's Thursday.
23,000 what?
576.
576 newtons. Whoa!
That's like super gravity.
Now, why do we have such a huge normal force?
Because your weight's so big and the radius is
Because our normal force is not just mg. What's our normal force doing? Our normal force is pushing us around the turn. So it's much larger than normal, right? Much, much larger than normal.
Oh my god. Oh my god.
We had Carter for 2 years. Sorry.
And also, notice that our normal force has to balance out some of this, well, at least in this, the friction force adds on to it, right?
Or does it?
No.
In the y direction. Well, it does from this equation.
Can I see someone's work?
I got a totally different number.
I got 14,325.
You got 14,325 for which?
For the friction force, why am I standing now?
Because you want to be heard. I got 14,325. All right, is this right, everybody?
Yes.
Well, we have two people that say yes.
I probably just like,
We have one person that says no. Is this correct?
I just probably did something
I probably
wrong.
did
I got
that.
1.3 each.
I got that. I probably did my algebra wrong. Probably.
Do we have three people that say this is right?
All
right.
right.
Okay, so is it possible then? Our friction force here is 12,852 newtons, less than or equal to mu force normal, which is 23576
Isn't
newtons.
that like what, 0.5
0.5-ish.
ish?
Is that possible?
I don't know, maybe.
You betcha.
Wow.
That's
this is
possible. Because tires
road.
have a coefficient of friction, I don't know, around 0.7, 0.8. If they're really sticky, higher than that. Okay? So you bet. You go around that turn at twice design speed.
I don't believe that's it.
Yeah, actually, yeah, I think it's possible. I've seen people do twice the speed of what they
Now,
recommend.
what helps though is the fact that it's banked. If this thing wasn't banked as much, notice what happens. If it doesn't bank as much, notice that when we're banked real high, the normal force and friction force work together to give us this force this way, right?
Uh-huh.
But if it's not banked as much, look what happens.
It
What do you?
depends.
It's almost all friction, right?
Friction.
And your normal force decreases because it's no longer giving you that inward force. So you lose by two methods. You lose because friction has to be higher and your normal force decreases. If your normal force decreases, you lose the ability to gain friction, right?
Yes.
So that's why you have bank turns in these races, because otherwise the races would be way slower. They have some tracks. Yeah, in fact, if you're, if it's banked at like 80 degrees, you can You can go fast, fast, fast as you can
So they could
possibly
like
go.
have it like this, and then you can just go as fast as you could around the whole thing,
Mhm.
like a little.
Like speed
But then if you go slow, you fall
Speed
down.
race.
Like
It
speed
would-
racer.
Would it
Can I ask you a
squish you?
question?
Yes.
About the algebra?
Would it squish you?
Mhm.
Okay,
So-
this will make it a lot easier if I can see it. Okay, this
Mhm.
is Fn, and this becomes
What
tangent,
if you were
right?
wearing a five?
Ah, wait a minute. This becomes tangent, but then you have MG over cosine theta.
Okay, so you have mg over cosine theta
Next, no, Gary
plus
commercial, what is G?
the
They had a
friction
teacher
times
this.
tangent,
Yes.
You did too.
and then when you plug that in, it's gonna be times sine. And this is where I made my mistake.
Most of those people.
Plug that in
Over
over.
here,
It'll be multiplied by sine, yes.
yes. So then you'll get mg tan
Right?
theta, and
MG
then
tan theta, and then you get a force friction sine tangent. Which is the same thing we have here.
Okay, oh, and then you just factored out the tan.
Yes, all I had, my tangent is factored out.
Okay,
That's identically the same.
okay, and then you factor that out. Okay, so I think that's where I made my mistake with my algebra. I messed something up.
Oh, okay.
Well, because I couldn't, I was just trying to see how you got from here to here, and then
Uh-huh.
I think when I was factoring this out, I multiplied something wrong. I think I put a sign over here instead of a tangent
That,
when I was
okay.
factoring.
Yeah, that'll, oh yeah, and a sine and a
I
tangent
just
at
need
40
this-
degrees will get you a big error.
I just needed to see how you
Sure.
factored this. Okay.
Works out good.
Yes, I got it now.
There are some tracks in NASCAR.
Like Talladega.
Well, no, Talladega has a big bank. But there are some of the older tracks that are smaller and flat. And the races are much slower because they cannot go around those turns real fast because they're not banked. Like for instance, Formula One, when they're going around the streets of a city, they speed up on the straights, but they have to slow way down for the turns because they're not banked.
Unless they do it.
Yes, unless they can drift. Now
Please tell me
in
we don't have to have.
Formula One, they don't drift.
They don't want to do this.
They don't want to drift. They can go faster in that environment without
Break
drifting.
it down anyway.
Plus, it'll be dangerous. They'll be knocking into other cars if they do that, I guess. I wonder why they don't.
It's a,
Bump
Tires.
tires.
It's a tire.
Yeah, you're probably right, because the tires are all
Different.
super sticky.
Why?
in the car.
Yeah, I got it.
That's true. If you're going to be drifting, you're going to be smacking into other cars, and those Formula Ones they're plastic and will fall apart, and then they lose their aerodynamics. There's one other type of circular motion problem that we're going to need to be aware of,
In 3 minutes.
and in 3 minutes, and that is the one where you go in a vertical circle. Object going around like this.
Like a Ferris wheel.
Yes. Now, remember at the top, like a Ferris wheel or a ball in the end of a string or whatever, at the top you've got tension or something down. If it's a ball in the string, it's tension, and you have mg. At the bottom, you have tension up and you have mg down. Where does tension have to be greater?
Down.
Bottom.
At the bottom, right? Now, not only does it have to be greater at the bottom because it's fighting mg, but it also has to be greater because of...
It's the turn and centripetal force. I mean centripetal acceleration.
Well, is the centripetal acceleration here and here the same?
Yeah.
Yeah, it should be.
Really?
No.
Unless it's in a ellipse. I'm confused.
Faster, slower. Faster, slower.
It's an ellipse?
Faster, slower.
I
Why is
couldn't
it-
tell if that was your circle.
No, it's supposed to be a circle.
Why
But
is
the
it
thing is
faster?
conservation of energy, where's it going faster?
The bottom.
At
Oh,
the bottom. Now, if it's a Ferris wheel, then the centripetal acceleration at the top and the bottom is the same, right?
It is?
Yeah, because it's all connected.
Oh, no.
And so it all goes the same speed
It's
all the
so
way
down
around.
at the top.
But if it's like a roller coaster car going around a loop, or a ball on the end of a string, it goes faster at the bottom than at the top, right?
Yeah.
So not only does the tension have to fight gravity, but it has to be much larger because it's going faster because your v squared over r is bigger. Okay? Now, everyone, they're going to ask you about this point. Which way is tension? Sure you do. Which way's tension?
To the left, to the left,
Which way's mg?
to the down, to the down.
The down.
All right. Which way is it accelerating?
The middle,
The middle left.
Thank you. Middle, left,
The
third
left.
quadrant, right?
And the left.
That way. Hey, so we have a centripetal acceleration and we have a tangential acceleration for a net acceleration of this way, right? So in this direction you would have t equals mv squared over r, and in this direction you would have mg equals ma, and your acceleration downward would be g, right?
Yes.
Okay. What if you're in this spot?
Magic.
Then you've got an mg down and you've got a tension this way. So which way are you accelerating? Out this way somewhere, right? Okay. So we could end up in some of those other locations that this year. Okay? All right.